Hello everyone. Welcome to the 22nd IDS Scholar Seminar Series. Today we are very delighted to welcome one of our own professors, Professor Yingyu Liang, Associate Professor at HKU Musketeers Foundation Institute of Data Science. Professor Liang will be delivering a lecture on tangram theory of generalization, rethinking machine learning via the lens of composition. So a little bit about Professor Yingyu Liang. He is an associate professor in the Musketeers Foundation Institute of Data Science and the Department of Computer Science at the University of Hong Kong. He is also an adjunct professor at the Department of Computer Science at the University of Wisconsin-Madison. Before that, he was a postdoc at Princeton. He received his PhD in 2014 from Georgia Tech and a master's and bachelor's from Tsinghua University. He is a recipient of the NSF Career Award. His research group aims at providing theoretical foundations for modern machine learning models and designing efficient algorithms for real-world applications. Recent focus includes optimization and generalization deep learning, robust machine learning, and their applications. Let us welcome Professor Yingyu Liang. Professor Liang, please.
Okay, thanks. Thanks for the introduction. So today I'm going to talk about towards the tangram theory of generalization. So unfortunately, it's not about how to play tangram, although I think it's pretty fun. It's still about machine learning, okay? It's still about AI. It's just like making a metaphor, showing that we may need a new way to think about machine learning through the way of composition, like putting different pieces together to achieve generalization to new tasks. So that's similar to tangram. What do I mean by that? So basically, we have seen significant progress in many different areas of AI, usually through machine learning approaches, in particular deep learning, right? Just different kind of neural network. So I'm just going to present some of them here, but most of you will be familiar with all those different kind of applications, right? But if we look at the theoretical intuition behind, it's actually not that much. Most of them are more like empirical intuitions. We do have very strong empirical performance and many different empirical observations, right? And a lot of intuitions from those observations and performance measurement, for example, scaling law. But if you think carefully, it's more like when you see a doctor, the doctor can measure the temperature, the blood pressure, measure different kind of things. They are descriptions, descriptive, instead of mechanistic, right? All those empirical observations don't tell you how the different kind of symptoms come about, what kind of disease, and how to cure the disease. Right? Here, in the context of AI, it's more like, okay, you do know a lot of things by measuring the input-output of the AI models, but you don't really understand what's going on underneath. Even inside the already trained model, it's already pretty hard to understand what's going on under the measurements of the performance, let alone the training process, right? Of course, in the old days, things seems to be somewhat different. Like we have the well-known statistical learning framework. Things are pretty clean and clear. Here is the classic IID setting, right? The most typical, most standard one for supervised learning. Okay. Of course, we can kind of generalize it a little bit to some other kind of learning settings, but this is the standing point, right? The starting point of using statistical perspective to think about machine learning. Okay, so usually we imagine that we are having some unknown ground truth distribution. We can call it a task. Okay, so the distribution is a task, and then we get a lot of experience from this task in the form of IID samples. We call them training data. In supervised learning is a pair of input and output, right? Okay, and then typically we are going to just propose certain kind of models, a model class like neural network or a linear classifier, or some other kind of things. And then we learn the model. By learning here, in particular in this statistical learning framework, we basically just mean picking one of the model among many different hypotheses, right? It's like you can kind of think it as a generalization of hypothesis testing. In hypothesis testing, you have two hypotheses and you use the evidence to pick one of them. So here you can imagine that you have many different hypotheses. Each hypothesis corresponds to one model that you can use. And then you just pick one of them, right? And usually by picking, we introduce some performance measurement here. It's usually called loss function, okay? Usually it's called loss function, and it's decomposed on each training data point. So we can just take the average of the training loss on the training data set, right? And then we just minimize this, just thinking like the loss function is a measurement of the quality. And then we just pick the best quality, okay? All right, and then we just applied it on future data, right? On future data, usually we imagine that the future data is also from the ground truth distribution. There are IID samples from the ground truth data distribution similar to the training data, all right? So this is the key assumption here. Essentially, we do need to have, if we want to have good performance on the future data, we do need to have some relation between the future data and the training data, right? Otherwise, if there's no connection, then we cannot imagine that we train on training data and then we get a good performance model on the future data that have no relation to the training data, right? So here, the relation is formalized as IID samples, right? Just the statistical relation is modeled by this unknown ground truth data distribution. All right, then our ultimate goal is not about training. Our ultimate goal in machine learning is just to get good performance on future data. Here is measured by the expected performance on the underlying ground truth data distribution. So this is the generalization. So all machine learning is just about generalization, right? All right, so if we compare this to what happened today, then we can think essentially they are very different from what we are actually having nowadays. It's a good theory for, let's say, support vector machine, a random forest tree, AdaBoost, those good old days machine learning models, but they are not, they do not capture well what we have nowadays, right? Beginning from a few years back, actually this figure is from 2021. So once we have, especially after we have the AlexNet and ResNet, especially ResNet, once we have the ResNet, people discover that we can just use ResNet as the backbone, as the feature extractor, and then extract the feature and then use it for all kind of computer vision tasks, also including some other tasks. Okay, so at that time, if you look at the conference papers, it's all about, okay, let me try to use this for this kind of application, and then I try the feature extractor for another application. Then you can just easily get publication by just extracting feature and then apply an application that have not been tried, okay? So, and later on, nowadays we can see that we further generalize this to other kind of data, in particular text data, right? Once we have transformer, actually before transformer, we also have some other efforts that are now overwhelmed by the history, but I kind of remember that after ResNet becomes so popular for different kind of applications in computer vision, the natural language people begin to think about, okay, can we do the same? Can we have a neural network similar to ResNet, but for text data, so that we can just use it as a feature extractor? Of course, they call it representation. They call it universal representation. Can we get a universal text representation? And then I can just use it for like all kind of the natural language tasks like syntax parsing, semantic analysis, and different kind of sentiment analysis, and so on and so forth. Okay, and there are many different kind of efforts. Some of them are pretty well known, but now less well known. Later on, transformers just take over. It's just essentially achieve the idealized goal of getting the universal representation for text, right? Nowadays, we just train transformer or similar kind of architecture, and then we can get performance, good performance on many different kind of tasks. So this kind of approach is summarized as a foundation model. Of course, there are many other names like pre-trained models or representation models and so on and so forth. But here, we just used the figure from a report from Stanford, essentially calling it foundation model paradigm. Essentially use a lot of data, including supervised data, label data, and also unsupervised ones, like just the whole like internet text data, and then do training to get a base model, okay? And then we do certain kind of adaptation to some specific task, usually using a few data points from the specific domain or task, okay? So this approach is called adaptation. Of course, nowadays we have different terminologies, like usually we call the training stage pre-training, right? And then the later on adaptation stage called post-training, which can include many different kind of things like fine-tuning, parameter fine-tuning or reinforcement learning, and also potentially later on, even in inference time, we can have test time computation, right? Or even test time training. Many different kinds of techniques, but roughly speaking, the main difference compared to the traditional approach that this time we no longer have the specific one, just pick one specific model for a specific task. Rather, we have a foundation model, a base model, and then we use it across many different kind of tasks. Although we need, we still need a little bit of adaptation, but later on, in particular for large language model, we find something even more surprising. We can actually do so-called in-context learning, meaning that the adaptation need not to be performed on the parameters. We can just describe in words what we want, just describe the task, the specific task that we want. For example, here, it's actually from a while back, right? You can talk to ChatGPT, say something like write a 100-word product description for 2020 kind of thing. Okay, so certain kind of product, and then essentially you get what you want here. You can ask him to write a rock song, right? You can ask him to write code. This is pretty old. So, but nowadays we can actually have much more advanced outcomes, especially using, for example, cloud for writing the code. But anyway, the key thing here is that essentially it seems like we now are making good progress towards so-called AGI, right? The industry people like that a lot, like this particular name, AGI, artificial general intelligence, quite much. It's kind of like suddenly we see some hope of achieving the general intelligence system that we really hope for. The idea is that we have a holistic big model that can handle many different kind of tasks at the same time, right? Essentially by training on many different kind of data, many different kind of tasks, right? For example, ChatGPT is trained on a huge amount of text data, and of course nowadays those large language models are also post-trained by, let's say, coding data to improve their reasoning performance. But anyway, the key idea is that we use a scaling law, just based on scaling law, which means that we need to use huge data and huge model and do a lot of training. And then we can get a large model that can handle many, many different kind of tasks, even including those tasks that may not have been seen during the training time. Right? So automatically we can get general intelligence. So here I highlight this general, right? So although in the when the notion of AI was first proposed, you can check that essentially those people were hoping for general intelligence systems. So the notion of AI was actually meant to be AGI nowadays. It's just because in the history, people discovered, okay, AGI was just too hard, just too difficult. We get into AI winter. So people step back, okay, just consider task-specific learning, like the statistical learning framework we just mentioned at the very beginning. Nowadays, it seems like, okay, we make good progress, so we can essentially hope to try to achieve the original goal of general intelligence, right? All right, so then we can see that from the more theoretical perspective, it seems that the main difficulty to understand what we have nowadays is that we cannot apply the statistical learning framework directly for modeling such kind of scenario, right? Like we cannot say that we have training data and test data from the same underlying ground truth distribution. Even when you believe that all the text data, for example, are coming from some underlying ground truth data distribution, which you can imagine encodes all the knowledge of humankind. If you believe the language is essentially the embodiment of knowledge for human beings, right? But if you think that, okay, if we train a model using all those kind of text data, and later on we use it for analyzing medical records, for example, it's hard to convince people that the distribution of medical record is similar to the distribution of the whole internet text data, right? So essentially, it seems nowadays we do have a training data distribution if you believe that there's a distribution. Okay, even if you believe that there's a data distribution underlying the training data, it's still a distribution that's very different from the test time data when we actually apply the large model on top of some specific task, right? So of course, not surprisingly, people have thought about going beyond this so-called same distribution or in-distribution learning, right? Like, what if we get rid of the assumption that the training data and the test data are coming from the same distribution? What if we allow that we have two different distributions, one for training, one for test time? Okay, so this is the traditional machine learning direction called domain adaptation or transfer learning. Okay, they have some subtle difference in the old days, but nowadays, at least for today's talk, let's just ignore the many different variants along those directions. Let me just briefly mention that the typical idea. Like basically, the idea is that we train on some training data, let's call that source or source domain. And later on, we apply on another target task. Okay, we call that target task or target domain. The two data distribution can be different, okay? But anyway, you just train on one and just directly apply on the other. This is the most naive form of data of domain adaptation or transfer learning. Okay, of course, when we do the theoretical analysis or empirically when we do experiments, the intuition is that we do need the two data distribution to be similar. Okay, usually you can use some distance between the two data distributions to quantify the error that can introduce by the distribution shift, right? Okay, so this is the, of course, you can also think about like, okay, you train on the source domain and then you do a little bit of adaptation using a few data points from the target task, okay? So there's what do we mean by adaptation, domain adaptation here? Usually a few labeled data points or a lot of unlabeled data points from the target domain, all right? So that's smarter, but when we do the analysis, either empirically or theoretically, we still require that this approach needs to have similar source domain and target domain. Their distance cannot be too different, right? Okay. And later on, when we have deep learning, okay, we can boost this a little bit more, boost this up using this approach. Okay, again, we have source domain, we have target domain, and then we use neural network, let's say ResNet, a backbone, to do the feature extraction. Okay, we get the so-called source feature and the target feature. All right, and then of course we can build a classifier on top of the source feature. Suppose we have good enough amount of source data. Okay, we get a classifier, and then we directly apply on top of the target domain. Okay, so this is a test image, and then we can apply it. From theoretical intuition or past empirical experience, we know that if the source feature distribution is similar to the target feature distribution, or if they have similar kind of distribution, their shift, the distribution shift is small, then the classifier usually works well, right? You can do theoretical analysis. But compared to the naive idea, right? Nowadays we have this extra component of feature extractor. So the idea is that I can fine-tune, I can train this feature extractor so that my target feature distribution is similar to my source feature distribution, okay? Do a distribution match, not on the original image domain level, but on the feature, on the extracted feature level. Okay, so the assumption now becomes, let me just assume that I can have a feature extractor that extracts important features and also make sure that the distribution of the target feature and the distribution of the source feature are similar to each other. And then I can apply the classifier trained on the source domain to the target task, all right? So this actually works much better than before, than the old naive model of directly training the classifier on the source image and then directly apply on the target image, right? Because the feature extractor now aligns the distribution. But you can see overall, the key idea is still to have similar distribution, right? But if you, again, you come back to what we have nowadays, think about ChatGPT, then it's very hard to believe that you can actually have important features for both the training data and the target task. For example, let's say the whole Wikipedia, the whole internet text data, and the target domain is, let's say, medical records, okay? It's hard to believe that, okay, you can have a feature extractor such that the feature extractor on one hand preserve important features and also have similar distribution, right? It's just because the pre-training data can have different kind of important feature, right? Even they are hidden, but you can imagine that even the hidden important features are quite different from the target task hidden important features. All right. So essentially, this kind of theoretical framework or the way of thinking doesn't match what we have right now. So how do we think about, how do we have a modern view of what happened right now in machine learning? Like, of course, if we think about a very high level intuition, like if you ask practitioners why you believe that ChatGPT trained on the whole internet, text data can actually handle some specific target task text data, they will say something like, oh, okay, it extracts knowledge from the pre-training data, and then later on they reuse those knowledge to handle the new task, right? So knowledge reuse essentially is the very rough idea But of course, it's a very vague intuition. If you want to mathematically formalize it, we need to think a little bit more. So we have some of the good examples that goes beyond the traditional domain adaptation idea and also the traditional IID sample idea, I mean the in-distribution idea, right? For example, in computer vision, essentially we can do multiple task training, right? The idea is that on each of the tasks, you can actually learn certain kind of important feature, okay? Think of like training a neural network backbone, right? On the first task, okay, so this is the first task. It learns an important feature, like, for example, color. If it learns a certain kind of thing, certain kind of important feature from the first task and learns another kind of thing from the second task. And essentially, so you can think of like it extracts an important feature from each different tasks during the pre-training, okay? Even more precise, let's say, you get one particular neuron that encodes the texture feature, okay? One particular neuron on your top level of the feature extractor that encodes that kind of thing, okay? And then you have another neuron that can encode the color. And then you have a third neuron that can encode the shape, all right? So this different kind of features are encoded in different neurons. Or of course, in practice, they are kind of like distributed across many different neurons. But you can think it in that way. Then after you finish training using multiple tasks, when you apply on a new target task, which may require all those three features to do the classification, okay? And then you suddenly discover that training a linear classifier on top of your extracted feature is not that difficult because you already have those features extracted. So basically the idea is that by training on many different kind of pre-training data, essentially you learn different kind of skills. For computer vision, it's like roughly speaking, it's different features, right? Different patterns. So you recognize different patterns. And then when you apply it on a new task, you can try to just combine those important features that are important for this particular target task, and then to achieve good performance, okay? All right, so this is like composing, just reusing basic skills. And of course, if you look at math or reasoning, then it's even more like significant. Like composition is essentially the nature of doing math, right? Or reasoning. So here is a very simple example, right? Suppose the model learns how to take the sum of two numbers, and it also learns the basic skill of doing multiplication. You kind of hope that the model can combine these basic skills to calculate a composition of addition and multiplication, like a mathematical expression. And for reasoning, for more general reasoning, like planning, it also involves multiple steps that may need different skills, right? So essentially, this is a pretty classic notion. People just call it composition. It's a very, again, it's a very vague description, terminology. Like it's similar to feature. The notion of feature in computer vision also reused in machine learning. It's a pretty high-level thing. But essentially, people just use composition ability to refer to the ability of model that can combine basic skills to accomplish complex tasks, okay? In general. Why it's very important for general intelligence is because people, like even in the very early days of AI, people noticed that, okay, if you want to achieve actual AI, I mean, for general different kind of tasks. There are so many different tasks in the world. We cannot hope to just learn them one by one using the in-distribution learning, right? We cannot just pick one task and then train on it and pick another task and train on it. Even when we assume that the model won't forget anything, but we need to train on each task individually. Then like mathematically, you can say it's exponentially many tasks. So we cannot handle that. But why we still have some hope to achieve general intelligence is because we believe that all those tasks have internal structure. They are composition of basic skills. There are some basic components that you can figure out, and there are also some composition approaches, like in general, you can say algorithms, right? There are algorithms that can take the basic skill as a routine and then handle many different kind of tasks, right? And we can implement that as hopefully we can implement it as a intelligent system, okay? That's what we hope for. Okay, so that's why composition is very important. It's essentially regarded as the key notion, right? On one hand, it means that you cannot do individually. You cannot learn the task one by one. Cannot handle the tasks one by one. On the other hand, it means that there are opportunity for us to actually decompose the task into basic skills and try to learn how to compose them. Okay. Yeah, it's a classic notion in the old days, AI, when the notion of AI was first proposed. Like here, I listed a few keywords. If you're interested, you can check those keywords and combine them with the keyword composition. Symbolic representation and the expert system, general problem solver, hierarchical planning, and so on, right? Notice that all this literature in the old days are before machine learning. So you can see that none of them actually talk about learning to compose. All they are saying is that, okay, let me try to build a general problem solver that exploit the composition structure of the task. Okay, but when I build a general problem solver, I'm building handcraft the problem solver by experts. Okay. Nowadays, we take the learning perspective, saying that, okay, let me assume that such kind of compositional problem solver exists, but let me try to learn it. I want to build such kind of compositional problem solver using learning on top of data. Okay, so there's an additional challenge of learning. Okay, besides the composition, how to figure out the composition structure. All right. So of course, let me go back. Of course, we can first think about like whether the modern large models actually have such kind of things called composition ability, right? When you play with the large models like ChatGPT, you kind of have a certain feeling that it can combine different basic skills, right? But there are actually more quantitative evaluation results. For example, here's one that actually proposed some evaluation benchmark called skill mix. All right. In general, they come up with many different queries for the large language model. Each query, like here is an example of the query. Write at most 2 sentences in the context of doing that illustrate all of the following skills. Okay, so it require 3 skills. Okay, and then you put this query to ChatGPT. The ChatGPT will produce this outcome. Okay, it will output this sentence. Okay, and then you take this outcome, this answer from ChatGPT, and hand it to another large language model, ask that language model to do the grading, to do the evaluation of the answer for you, okay, according to certain rubric, okay? And then at the end, you can get an evaluation score, right? So basically, it essentially I think it enumerates something like 100 different skills and generate many different such kind of queries, and then do the grading on top of many different models, small models and also large models. Essentially, in summary, it turns out that the small models struggle on such kind of evaluation, but large models like GPT-4 can actually handle such kind of composition pretty well, up to 5 skills, for example. Okay, like even when you ask GPT-4 to produce outcomes that combines 5 skills, it can still handle. But for small models, like 10 billion parameter models, they struggle with even combining 3 skills, okay? All right, so this is essentially evaluating the current models just out there. But of course, you can do a little bit more, right? One step further is, can I train the model such that it can handle such kind of composition? Basically, can I fine-tune the existing model such that it has even better composition ability, right? Actually, this is something pretty interesting. Essentially, okay, if we go back here, essentially each query actually contains a few keywords. Each keyword corresponds to a skill, right? And it also contains a topic. Okay, here is a sewing here. So basically, they have a synthetic generation approach for generating such kind of query. If you give the generator, the query generator, a topic and a few skill keywords, then it will generate that kind of query. So what they are going to do is come up with a set of topics and a set of skills, roughly 100 skills, let's say, something like 30 topics. And then they divide into training skill set and held out skill set. Also divide the topic into training and held out, okay? And as you can imagine, first they do the training using the training topic and the training skill to generate a lot of queries, okay? And then use the query to generate and put it into GPT-4 or large models that can handle such kind of query. And then you also do some grading and filtering, essentially just get the high quality, high score outcome, right? Then this is the training data, essentially. And then using the training data, you just try to fine tune a small model, like 30 billion llama 2, 7 billion mixture model. All right, so you just train this, and then after training, you just evaluate it on the held out set. Okay, so notice that the key thing here is that we do have completely different topic and completely different skills for the training and test time. Okay, so this is really trying to learn the composition algorithm. It's not about learning a particular composition, like particular composition or composing these 3 skills. Here is trying to say, let's try to learn the algorithm to do composition. The algorithm that allows the model to pick skills and compose them to accomplish a new task. Right? It turns out that actually it can work pretty well. Even small model, after fine-tuning, can handle such kind of new task. Even the new tasks are completely different, unseen in the training. Okay, so this is what people call task generalization, right? Is corresponds to what we are actually most interested in. All right, and this is one line of work. That is one line of work that directly evaluates this like composition ability of large models. And recently, there's actually another line of work on studying the effect of reinforcement learning for reasoning ability. Right, after DC, using the open source their model and their training method, saying that okay, you can do this kind of reinforcement learning. Usually the approach is first do a little bit of supervised fine-tuning, and then do reinforcement learning, right? And then you can get a good boost. You can get very good reasoning ability improvement after reinforcement learning. And then people are very interested in comparing the effect of supervised fine-tuning and reinforcement learning, these two steps. What are their effects on the reasoning ability of large models? And somewhat surprisingly, later on, recently, it turns out that people begin to think about this line of work from the perspective of composition. Okay, let me first briefly mention. Essentially, people kind of like, as you can imagine, immediately people think like, oh, okay, after doing supervised fine-tuning, when you put the model on top of the reasoning task, it performed poorly. After then you do reinforcement learning. After reinforcement learning, the reasoning ability, the performance on the reasoning benchmark gets much improved. Of course, it's the effect of reinforcement learning, right? But then this paper, interesting paper, comes out saying that, okay, does reinforcement learning really induce reasoning ability, okay, beyond the base model? What I discovered is that if you, like, okay, before, let's say, after supervised fine-tuning, before reinforcement learning, okay, you do the reasoning, then the evaluation is usually just check the top one outcome, the top one output sentence. But if you allow a little bit relaxation, you check the, let's say, top 10 output sentence, okay? Here, top 10 means according to the output probability of the large language model, okay? It turns out that usually the correct answer is not within the top one, but it's within the top 10. Okay, if you go even further, let's say something like top 30, essentially it can match the top one performance of the model after reinforcement learning. And furthermore, the top 30 performance of the the SFT model is comparable to the top 30 performance of the reinforcement learning model. Okay, so then it kind of seems to suggest that, okay, the reasoning ability was already in the base model after supervised fine-tuning before reinforcement learning. The effect of reinforcement learning is just boost the probability of the correct outcome, right? So basically, it doesn't have new capacity. Basically, the argument here is that reinforcement learning doesn't introduce new reasoning ability. It's just boost up the probability. Of course, it's still very useful, but the important thing is that it may not generalize to new task. Okay, that's their argument. Like, okay, it may not be that. But of course, another view is that supervised fine-tuning actually memorized quite a lot of tasks. It doesn't handle new tasks. After doing a supervised fine-tuning, you can handle those tasks that you have seen in the supervised fine-tuning. But if you give it a out of distribution, different kind of new task, then usually it doesn't work well. So that means SFT memorizes. Here memorizes doesn't mean memorize the training data point, it means memorize the task, okay, roughly speaking. Okay. On the other hand, if you do reinforcement learning, you notice that actually it can handle those OOD tasks pretty well. You get improved performance. Okay, so this is like a pretty example paper along this line, but there are many other papers. So this okay. All right. So recently, recently there's a new perspective from composition saying that essentially the idea is that after doing reinforcement learning, actually the model learns new skills, but it only learns those new skills that are composition of the old ones that have been seen in the supervised fine-tuning. So it means that, okay, it does generalize instead of memorizing the old skills, but the generalization is only by composition. Okay, it doesn't mean that it can handle arbitrarily new tasks. I think that it's pretty good example of how to do the composition here. What they are doing is something like this. Essentially, they come up many different functions like this. Okay, essentially the input is a string of text data. The output is doing some processing of the input string. Let's say capitalization, so making all the lower cases into upper cases, like this simple, or reverse the order of the tokens, some simple kind of operation. They come up with something like 30 different functions. Each of them are regarded as a basic skill, right? And then you can have atomic tasks, which each task is only about one function, one skill. And you can have compositional tasks, okay? It's just function composition, right? Okay, so it's directly here composition actually have the exact meaning that we have in math, just function composition. All right? And then using such kind of benchmark, you can imagine you can use them to evaluate the model before reinforcement learning and the model after reinforcement learning, right? Okay, and this is exactly what they are doing. And this is what they confirm. Of course, at the very beginning, it's proposed as a hypothesis, but their experiment just confirms this hypothesis. Okay, so we have a base large language model after pre-training, before supervised fine-tuning. And then they do what they call NTP. Okay, roughly speaking, it's just a supervised fine-tuning. Okay, and then you get this model after supervised fine-tuning, before reinforcement learning, right? And they make sure that you have seen these basic skills, right? That basically means that as the supervised fine-tuning use those atomic skills, just one function, to generate the data and use those data to train, and then you get this model. So this model, after supervised fine-tuning and before reinforcement learning, knows all the atomic skills, but it doesn't know the compositional skills. You can evaluate it and find that, okay, indeed, it's like this. And then if you do reinforcement learning on atomic skills using only one function for each task, okay, at the end of the day, you discover that, okay, after doing that, you only know atomic skill, you still cannot get compositional skills. But if you reinforcement learning on the composition of, let's say, 2 basic skills, right? You should randomly sample 2 basic skills, compose them, and then do reinforcement learning on top of such kind of data. And after that, you discover that such kind of reinforcement learning actually allows you keep the atomic skills, and it generalizes to other kind of compositional skills. In particular, it generalizes to some skills that have some composition that have not seen during the training. Okay, you can also actually what they did is similar to the held out set I just mentioned. You held out, you divide the skill set into 2 parts. One is for reinforcement learning. The other skills are for this evaluation. And then they discovered actually, yes, after doing reinforcement learning, you can generalize to new compositions of unknown skills, okay? And even generalize to composition of more than 2 skills, all right? Yeah, here is just the concrete outcome, summary of their concrete outcome. But essentially, it's just like, I believe that this figure here just summarize very well what they discover. So it seems like, importantly, it seems like reinforcement learning actually allows you to learn a meta algorithm of doing composition. I mean, the model after reinforcement learning knows to pick what kind of skills and then knows how to compose them properly to handle the task, handle a new task, a new composition of new skills. But of course, the important thing is, another important thing is that the model before reinforcement learning must know the atomic skills, right? Okay. If you evaluate it on some composition of completely new skills that have not been seen by either supervised fine-tuning or reinforcement learning, then it cannot handle that. Okay, so so they summarize in 2 conditions. One is that the model before reinforcement learning needs to know the basic skills. And then you do reinforcement learning on composition tasks so that it can learn how to do the composition. Okay? And then it can generalize to new composition of even unseen skills. Unseen compositions of that have not been seen in training, either supervised fine-tuning or reinforcement learning. Okay? So these 2. Then supervised fine-tuning is very good for teaching the model the basic skills, right? And the reinforcement learning is very important, crucial for teaching the model how to do the composition, how to compose, okay? All right. Okay, so this seems to leads to this tangram analogy of composition, right? So in tangram, you actually have 7 pieces, right? And then you have a target task. So these are the basic skills, and these are the target task, okay? And then you can just try to pick the correct composition of the correct pieces and put them together to get a solution for your target task, okay? So this is the analogy here. All right. Okay, so it seems to me that I've haven't gone into what we have done. So I'm going to go quickly on top of this. We actually also done some study, but in context learning, meaning that we have not seen the skills. The model have not seen the skills, but we are going to explain those basic skills using in-context examples, right? Okay, in the query, we are going to have K1, K2 examples from some basic skills, and then we also have some demonstrations of composition tasks, and then we check whether the existing model actually have such kind of ability to handle this kind of in-context composition, meaning that, okay, the basic skills are also in context, okay, needs to learn on the fly. So, okay, let me quickly go over. So this is an example, like the basic skills are doing composition, doing swap of the words, and so on. So basically some very simple linguistic task, all right? And we test, essentially we can see that if we increase the number of composition task examples, as expected, we can get better performance. But the important thing is this: if we increase the number of simple task examples, it actually in general hurts the performance instead of helps the performance. Okay, like usually we expect that if we give more data, the model will get better performance, right? But this is not the case for this particular in-context composition. So we check a little bit why that happened. We look into the output of the models and discover that basically it's because like it just doesn't recognize the composition query. Right? You ask it to perform the composition, but it only performs one task. For example, only simple task 1. And in particular, when you increase the number of in-context examples from task 1, from simple task 1, then the model will likely answer the composition task query by only performing task 1. Okay? It means that the model is trying to retrieve the, trying to figure out, trying to match the query to the examples. If you have more simple task 1 examples with higher probability, the model will match the query to simple task 1, and then it only performs simple task 1. That decreases in performance. Okay, you are supposed to first perform simple task 1 and then simple task 2, but here it only performs simple task 1. All right. So it turns out that here we have the model doesn't have such kind of in-context composition, basically because it doesn't know how to do the composition properly. It doesn't retrieve the correct basic skills. But if you go back to the skill mix experiment, you will notice that they give very explicit text description of what kind of skills to use. Here is different. Here we use pretty abstract. We use abstract notations, something like special symbols to denote the operation that we want. So it basically means that the model doesn't have explicit ability to retrieve the correct basic skills in this setting. Like if you have very explicit hints, then it can do that. But here it doesn't do that, okay? Right, okay, so let me, we do some further ablation study and discover that it retrieved the corresponding skill just by doing pattern matching, okay? How we do the ablation study is to introduce an irrelevant task, something like this, and then you just ablate the operators, right? The operators are parentheses or the sharp notation which corresponds to the basic skills, which indicates the corresponding basic skills, right? Or you can ablate the content. It turns out that after you remove the operator and replace it with some random noise operator, it affects the performance larger, more significantly. So it means that the model actually relies on the operator rather than the content. Okay, so the model does have a lot of limitation in retrieving the correct basic skills. Okay. All right. So this is the basically what I mean. After you blade the operator, then essentially you get very different outcome from the original figure. Okay. All right, so I think I'll go with time. So I briefly mentioned some existing theoretical work about how to model composition. So here is a one from one of my old friends back in undergraduate graduate study. So they propose basically just model the composition as a computational graph, right? Like each node in the graph is just corresponds to a function. But in their paper, they essentially just require that all the internal nodes use the same processing function. They don't allow different. I don't know why. I asked him, he said just for convenience. But anyway, they don't really talk about how to learn. They just, in their paper, just study that, okay, like let's say convolution neural network can be regarded as such kind of composition graph, okay? And they also talk a little bit about learning, but don't talk about how to learn the graph. Just assume the graph is given. But as we mentioned, like this is essentially the key, right? We hope the model can actually learn the composition algorithm, actually encode an algorithm that algorithm corresponds to how to pick, how to compose the basic skills. All right, so there's another interesting paper called task generalization. It's just from training on one set of tasks and test on another set of tasks. And in their structure, in their paper, they proposed this theoretical framework essentially show here. This is very similar to what happened in large language model. At the very beginning, you have X, the input sentence, and then you use some function to process it to get next word, Y1. And then from X and Y1, you get another word, Y2, and so on and so forth. And until the end, you get YT. Okay? So this is similar to, so that's why they call it autoregressive compositional structure. But I assume that you have theta 1, theta 2, and up to theta t minus 1, such kind of thing. And each theta is regarded as a basic skill, okay? And then how do you do the training? Okay, here training is actually somewhat different from our traditional training. What they mean by training is that you get a lot of tasks, randomly sample a lot of tasks. Each task is just corresponds to a set of randomly sampled theta 1 up to theta t, okay? Okay, you just apply these thetas to generate the data, okay? And then you get the data from this task. And then you sample another set of theta 1 up to theta t randomly. Like here, uniformly at random, okay? And then using such kind of tasks and their data, they try to learn the skill set theta I from a larger set, okay? Essentially, what they are doing here is actually to learn the basic skills. They learn the basic skills. After you figure out the basic skills, in inference time, you get a new task, theta 1 tilde up to theta t tilde, and then you get data generated from this task. And then, as you can imagine, using the data generated here, generated from this new task, you can learn this theta 1 tilde up to theta t tilde from the identified skill set in the training. So it's more like this is pre-training. The inference time is the actual adaptation, fine-tuning, right? And then what they show is that here during the pre-training, you actually only need D so many training tasks, where D is equal to the size of the atomic skill set at each step, okay? So the number of new tasks can be D to the power of T, right? So basically this means that using linear number of training tasks, you can generalize to exponential number of new tasks, okay? Which is an interesting paper here. Okay, here is another paper which essentially have similar kind of formulation. They call it autoregressive chain of thought, but essentially it's just what we just seen. Okay, you have an input, and then you predict the next word, and then using the input and the next word, you predict the second word, so on and so forth. So this is what they call train of thought. It's just the same thing as before. But this time, they assume that you only have one holistic model, F, for all the steps. But here, you can see that they have theta 1 up to theta t minus 1. But here, they assume only one holistic function F, right? That function needs to be very large, even knowing like when to pick which atomic skill, right? All right, so essentially they get some sample complexity bound similar to before. All right. We also have some preliminary theoretical results from our own analysis, but I briefly mentioned. So for me, like composition can, about composition, we can talk about two things. One is learning a function. And the function that we try to learn is a composition, right? For example, here, let's say the target function we want to learn is a composition of few basic skills, like ft up to f1 here. And then if we only given examples in the form of x and the output of the whole function, right? Then by basic standard analysis, essentially the important thing is that the arrow is linear in the number of steps, t, right? If you have more composition steps, then the arrow will be larger. On the other hand, if you do know the intermediate outcome, like similar to trade of thought, right? The intermediate outcome of the composition steps, then essentially you can get rid of the linear dependence on the number of steps. It means that you can handle very long trade of thought if you have intermediate outcome for learning, right? That's the effect of trade of thought. So this kind of result is very similar to the existing theoretical work that I just mentioned in the previous slides. All right. But the other thing is what we are trying to do right now is the model how to learn the composition algorithm. Instead of one fix, like here, notice that here is here is one fixed composition. But if you think about a skill mix experiment or the comparison between supervised fine-tuning and reinforcement learning experiments, what we really care about is whether the model learns how to do the composition, not just one composition function, like how to do the composition of many different basic skills to get many different new composition, right? That's the much more interesting thing that we are trying to handle right now. Right? So here is a very basic setup that is almost naive. So let's say we know the atomic skills, right? That hypothesis set, and then we have different composition algorithms, candidate algorithms. One of them is the one that corresponds to what we want. All the others are just hypotheses, right? Let's call them schemas. Essentially, you can think of them as a computational graph, right? Here, you have this computational graph composing F1, F2, F3, and then you get a new function. Here, you have a different computational graph. On the same set of atomic skills, you get another new function, right? A G prime. All right, if you say that for different computational graph, we can distinguish them up to accuracy epsilon 0, all right, then essentially we can do similar training, right? Randomly sample a lot of skills, compose them using the ground truth composition graph and get the data. Let's say get n data points from each of the m training tasks. Each m training tasks correspond to applying the ground truth composition on top of a set of randomly sampled skills, F1 up to Ft, all right? And then in inference time, you can imagine that we just get data from a new task, applying the ground truth composition algorithm on top of a new set of skills, right? So this is what we care about, like, okay, you learn using composition of many existing skills, no skills, and in the test time, you handle a new composition. And I would like to learn the composition algorithm G, okay? Then of course, here in this very simple setting, you can actually show that assuming there are finite hypotheses here, once we assume this is finite, essentially we ignore all the structure in this among this hypothesis set for the composition. Then by basic standard learning theory analysis is just log of the size of this hypothesis is enough from the training data here. But here, one thing I would like to mention is that we assume that the basic skills F1 up to FT is known. Basically meaning that when we are given the training data says that, okay, this training data is by composing these skills, right? If we don't have this assumption that the skills are known in the training data set, then things would be more complicated, okay? All right, let me just stop here and go well over the time. Okay, yeah, thanks.
So are there any questions for Professor Liang? Yes.
Hi, Professor. So thank you for your fantastic talk. And the results presented today are mainly about the composition of predefined atomic skills that can achieve significance performances. And I'm very curious about what's the outcomes if we cannot explicitly define the basic skills, or there are thousands of ways to define the atomic skills, or thousands of atomic skills, such as in the complex robotics tasks.
Yeah, that's a very good question. Essentially here, like for example, here, as I mentioned, we assume that we already have a hypothesis set of atomic skills, but that's not true in practice, right? And actually, that's the key bottleneck, one of the key bottlenecks. To think about that, actually, I would like to briefly introduce one good view about composition, a new view. Like, learning is equivalent to compression, right? Like even theoretically, you actually have the theorems showing that compression is roughly equivalent to learning up to log n, a log factor. It's the major open question, but anyway, it's roughly speaking that. So, like if you think about computer vision, compression is pretty straightforward to understand, right? Like you learn those important patterns, right? For example, sparse coding, right? It's a explicit form of compression. If you think about sparse coding, you learn those patterns that are important, and then you have some ways to compose those important patterns back into the original, right? Back to the original image. So you can think of the coding, the sparse coding scheme, together with the code patterns. I mean the code book, together with the sparse coding composition algorithm. They form the compression, right? And more generally, if you think about convolutional neural network, all the features, right, from the low-level Gabor filter-like feature up to the high-level texture-like patterns in the ResNet, let's say, you can think of it as a hierarchical compression, right? Now, back to composition here, you can think of the basic skills as compression, right? There are so many tasks in the world. Right? All of them requires a certain kind of algorithm to handle that kind of task. But there are subroutines among all these different algorithms that you can reuse, similar to how you can reuse Gabor filters for image classification. So here, for handling different kind of tasks, the basic skills are essentially the pattern, right? The pattern. So from the view of compression, you can think essentially on the most high-level view, even forget about mathematical formulation. What we think about composition is that you have a Turing machine, and then you would like to figure out a lot of the subroutines. I mean, small Turing machines, Turing machine. Let's use the word algorithm. I think that's easier to understand. So essentially, you would like to find an algorithm, and then you also would like to find a lot of the subroutines that you can piece them up, similar to the pieces in tangram, right? And then you piece them up in different ways. Okay. So there are two things. One is the the pieces, the components, the subroutines here, and then the composition algorithm. These two key things. Of course, from the modern view, like algorithm is also data. So essentially, all these things are parameters. All of them are data. But essentially, you would like to think it in this particular way. So from this viewpoint, immediately you realize that if you don't know predefined atomic skills, it's actually the bottleneck for learning the compression. Similar to like back in computer vision, right? Why deep learning is so, why ResNet and deep learning approach is so powerful for computer vision is that we can get rid of the handcrafted features. Like we don't need SIFT, we don't need HOT, we don't need those famous handcrafted features anymore. We just run and then it figure out those garble filters and even more sophisticated text-like features and shade-like features and so on and so forth. So the power of deep learning for computer vision at least is the way that it can learn, it can compress, it can figure out those component patterns and do a hierarchical composition. And we really hope the same thing happen here for more general intelligence, right? For many different kind of tasks, we kind of hope that when we train on top of them, the model just automatically figure out the atomic subroutines and even use them to build hierarchical structure of more and more complex skills. And finally, get a very complicated Turing algorithm that can handle more and more, or even like general kind of tasks. So the learning of atomic skill is essentially the key bottleneck. So that's why I say this is pretty naive, because we assume that they are known. Right. Yeah.
So any other questions? Yes.
Hi, Professor Liang. Thank you for your talk. I actually also want to ask about the composition ability in embodied AI, because in embodied AI, we actually want to learn from large language model that way. Once the data reach certain level of skills, the model reach certain level of skills, we can have this compositional ability. But for embodied AI, do you think the bottleneck of the compositional skill is also from the data? And if yes, how can we make this model composition? Do you think by improving data quality or other ways might make those embodied model to be compositional?
Yeah, so if in robotics, the notion of composition is almost always there, like different from other area of machine learning. We forget about composition for quite a while, just focus in distribution learning. But for robotics, like the out of distribution is almost always the case. So yeah, like composition is essentially always the key for robotics. And then in general, I would like to mention that here essentially one thing that are very important for learning how to do composition is the trade-off thought. I mean the intermediate outcome, right? So if you have intermediate outcome, even for supervised learning, let's forget about reinforcement learning. Even just for supervised learning, if you have intermediate outcome, you can decrease the error linearly, which corresponds to you can handle exponential number of tasks, okay? Using linear number of tasks. So you can essentially, in the context of robotics, it means that if you train on a few scenarios, you can handle a lot of unseen scenarios, essentially. So intermediate outcome is the key for doing such kind of learning. Although for reinforcement learning, it's also similar. The intermediate outcome is called reward, right, in reinforcement learning. And the key practical challenge, I think a lot of people would agree with me on this particular point, is that right now, why robotics is very hard to train and we need a lot of tricks on reinforcement learning is because the intermediate reward is very sparse. Okay, you can kind of say, okay, I can ask for reward, but the reward usually is negative, right? Meaning that only when you reach the end, you get a positive reward. You know how to do that, right? And for example, in robotics, when you ask the robot to pick up a cloth, for example, right? Like even when you miss just by a little bit, it just fails, and then the whole system collapses, right? Basically, in machine learning point of view, it means that you take a slightly off action, right? You slightly off, and it immediately leads to completely failure out a reward, like very large, very negative reward. And then it means that you have no supervision at all for this data point, for this data trajectory. So that's the key thing in the key challenge in robotics. You just don't have enough reward. I mean, corresponding to the intermediate supervised signal here. And I think the people right now are coming up with many different practical tricks. For example, you can do demonstration even in the middle, right? Like after the robot operate for a while, you can actually propose different alternative actions and try to compare the alternative actions. For example, compare the actions suggested by an expert to the actions suggested by the current model, and then try to update the model to, like, for example, such kind of thing. Is essentially I believe the key thing is how to make sure that we get intermediate supervised signals for robotics. Right now it's just too sparse. You cannot hope for generalization by composition, right? Like for composition, you kind of need a lot of intermediate supervision, yeah.
Any other questions? So I have two questions.
Yeah.
One is a theoretical question, another is a philosophical question. For the theoretical question, on the very first slide, you mentioned distributional similarity. Is there a specific definition for that? Is like that conditioned on some kind of
Yeah,
distributional?
think of KL divergence, TV, total variation distance. I think people have used those. More precisely for domain adaptation, there is an explicit seminal work that use explicitly the H distance. Okay, it's a specific definition of distance between two distributions. And then the error bound is essentially like, okay, the error is bounded by the error on the target domain is bounded by the error on the source domain plus the distance, the H distance between the source domain and the target domain. And there are many different variants of such kind of bound, but essentially you can come up with such kind of thing. Yeah.
But for continuous distributions, would you use something like a kernel discrepancy between two distributions?
Yeah, you can try to do that, but I mean, the H distance I mentioned can also be applied on continuous distributions. Yeah.
Okay. Awesome. And last question is a philosophical question. So in the slides, you showed an example where the LLM was learning to compose code and composing atomic examples of code as function. But in my view, that's a very anthropic view. Is there any reason why we should believe that functions as defined in a large language model are similar to what humans believe functions are?
I may not understand your question.
Yeah. So
yeah,
we can discuss later after lunch.
Okay, sure. Yeah. Yeah. Any other thing? Yeah.
Yeah, so we do have a group photo with Professor Liang at the very end, so please stay. And thank you for attending the talk today.
Oh.